Okay, let's do simple harmonic motion right now. And yeah, and this is a lot of fun. As fun as a topic in physics can be. Ooh, that's gonna bother people. Let's fix that.
What, the color or
the fact that it was tilted. Especially the type of people that watch these videos. You know what I'm saying? So for short, SHM. And simple harmonic motion is a regularly repeating motion. Oh yeah. So it's probably best to just say some examples of things that do SHM. A pendulum does SHM. And that could be either a string pendulum or a spring pendulum. So what are those? Well, I think most people are familiar more or less with a string pendulum. And we sort of did a demonstration of a spring pendulum. But basically, if I take a mass and I hang it from a long string or a rope and I release it, I will find that it will oscillate back and forth. It'll swing. Okay, so there's a spring pendulum. So yeah, I'm not sure how exactly to attribute that, but it's called watery gray halcyon. I don't know why. So the question is then, this is oscillating back and forth. So the first question is, what does the word oscillate mean? What does oscillate mean? Anybody know? All right, so it just essentially just means to swing back and forth about a central point. Okay, and that's sort of like a lay definition of it, because we would also consider something like a spring pendulum as also oscillating. So I'm going to draw a spring pendulum so you get an idea of what I mean. So let's say we have, and let's say we're looking down from above on this situation. Let's say you have a mass, and we'll make a mass. Okay, there's a mass, and we'll put two springs on either side of the mass. Okay. And we could say then that this right here is the central position. So this is displaced a little bit to the left of center. If we pull this over here and we release it, we'll find that it starts to oscillate back and forth, back and forth, back and forth. So you have to imagine that this is looking down on an object that's, say, on like an air table or some table with like really low friction so that it can move back and forth. Okay, so I'm going to take this thing and I'm going to turn it over. Group. I'm going to make it a little smaller, which I think I can do. And I'm going to draw it in some different positions. Okay? So we'll say that that is sort of like the, I don't know, the basic position. Oh, this isn't going to work very well. Oh, maybe it will. Hang on. Let's see what I can do. Group. Okay, yeah, that's good. I like that. So I want to avoid having gravity play a role here. All right. So if I imagine I'm looking down at this, okay, then I'm going to stretch it off in this direction. But let's think about what's happening with the forces here. Okay. If I stretch it off in this direction, the force on here, you can imagine, right, is going to be back in this direction, right? This spring is stretched. It's going to be pulling it back in this direction. And we're going to have what's called an amplitude. An amplitude is its displacement from neutral. That's considered to be positive, okay? Quite often, the amplitude is denoted as a delta x, okay? Delta x. This is going to represent the direction and the size of the force, okay? Right here, we can imagine, and this is F net, by the way. This is the net force on the object, right? The net force. In the very center, you're going to have forces that are acting equally and oppositely. So you're going to have force up and force down. They're going to be equal based on these springs, assuming these springs are equal. So in this case, then, the net force is actually going to be 0, because those will cancel out. F net equals 0. So when it's in its neutral position, the net force is 0. When it is maximally stretched in the positive direction, it has its maximal negative force. And therefore, what goes along with force via F equals ma is it has its maximal negative acceleration. So we'll also add that in. Okay? Its acceleration is down. And there's one more thing that we haven't yet talked about, and that's velocity. Okay? Its velocity at its maximal positive displacement is 0. So why don't we collect all these things at the bottom? Okay? We'll say F equals 0. And we'll say at this point it's moving up, right? It's on its way up. So V is positive, okay, and it's max. V is positive and max. Acceleration is equal to 0. Displacement is equal to 0. No problems there, right? That'll make sense. Pretty easy to follow. F here equals negative, and it's max. When we're at our maximal, we'll assume this is the maximal amplitude of this thing, or the maximum amplitude. Velocity at maximum amplitude is 0. Acceleration is negative and maxed. And displacement is max, positive. Actually, I shouldn't write max in there. And I should also call displacement delta x too, just to keep keep everything logical here. So F equals 0. Your velocity now, assuming time travels this way, is in the downward direction. Okay, so V equals negative, and it's maxed out. Acceleration equals 0 because force equals 0. And your delta x is 0 at this point. Okay, now we're going to move on to the next position. Okay, so now we're in the bottom here. So we've got our maximum upward force now, our maximum upward acceleration. We've got a velocity of 0, and we have a maximum negative displacement. So let's write that all down. F is maximum and positive. Velocity is 0. Acceleration is maximum and positive. And delta x equals 0. And then we're right back where we started again. Yeah, sorry, delta x is wrong there. Let me fix that. So anywhere in nature that you can set up a situation like this, and what I'm getting at here is a situation where the restoring force is proportional but opposite in direction to the displacement, you will set up simple harmonic motion. So the key equation that sort of describes all this stuff is this. SHM happens if delta x is inversely proportional to the force. Yeah, my bad. Not inverse. Proportional to the negative value of the force. In other words, when you have a maximum positive displacement, the force is also maximum at that point, but in the opposite direction. Yeah, sorry, not inverse. I said inverse, but I meant negative. Displacement is proportional to negative force, or force is proportional to negative displacement. It sounds weird to say that, but that's what it means. So what we've drawn here, what this represents is one complete oscillation, which happens when we return back to our initial position, okay? You can kind of see how you could like overlay here. Let's see what you could kind of overlay a sine wave on here. And when we get into actual like water waves or like waves in a coil spring, we will see that the wavelength is represented by one complete oscillation or one complete cycle. Okay? Cycles, oscillations, etc., have some math that goes with them. Okay, so I want to lay down some terms here. The first thing that we need to talk about is, of course, I don't like that, is amplitude. So amplitude is just simply the maximum deviation from rest. And that applies to string pendulums, spring pendulums, and waves. Okay? Amplitude, max deviation from rest. And actually we'll tie in some circular motion as well and just show how that ties in. But it's sort of straightforward, really. If you guys have done your like unit circle stuff and all that, you're probably already like anticipating what you're going to see there. So we've got that. Cycle equals one complete oscillation, which is what we kind of diagrammed above. Consider that one complete oscillation. Equilibrium is just its rest position. So remember, too, amplitude is just in one direction. It's not the total displacement from the bottom to the top. It's displacement from rest. Okay, so equilibrium is rest position. Period is time for one cycle. And last but not least is frequency. Is cycles per second. So go back and we'll state what units we would use for these things, if they're applicable. So A is amplitude measured in meters. All MKS, right? One complete oscillation, you just have to view that. Equilibrium is the rest position. Okay, that's pretty standard. There's no special thing for that. Period, though, is shown with a T for time, and it's measured in seconds in MKS. And frequency, which is an F, is measured in the per second. So it's the unit is per second, but that has a name. Does anyone know what it is? It is hertz, correct. I feel like there's a joke in there. Hertz has the symbol HZ. So anything happening cyclically or in a cycle, and the number of times it happens per second is always measured in hertz. Okay, so you see that in like radio waves, or like if you're talking about like the cell phone bands and so on, you hear things like gigahertz for like the speed of a computer and so on. Or you'd hear like a 60 hertz refresh rate for a monitor. just means it's refreshing 60 times per second. So it can be used in a lot of places. Anything that is doing SHM or repeating periodically. So you might notice here that frequency and period have an inverse relationship. So you can say T is equal to 1 over F. If that's true, F is equal to 1 over T. As frequency goes up, right? As frequency goes up, it's happening more times per second. The amount of time it takes must therefore be going down. Okay, so I just want to quickly look at some data that we actually generated. So this is the position of our bob, of our oscillating spring that we had above, right? But this is like data sampled like 20 times per second. So you can see that it generates basically a really nice sine wave. And you'll also notice that we had a force sensor connected as well. So you can kind of like figure out, if you're having the bob go up and down, how it correlates back to what we were talking about earlier, all right? I'll let you guys work on that on your own and think about that a little bit and think about why it is and how it is that these things are offset from each other, okay? And I also want to talk about how you would generate these things with a spinning circle, because the relationship between these things and a spinning circle is sort of interesting. So if we put a circle right here, and don't worry, I'll find a little animation for this, but I just want to kind of draw three things here and see if we can make sense of how one thing can create another, right? A bobbing pendulum and a circle don't seem to really have a lot of things in common, and yet they can both be used to generate a sine wave. Sorry about the chowder on the bottom. I'm not sure why those aren't nice and smooth. Something happened with our setup that we used, which by the way was more or less a spring pendulum like this, although it was actually just a hanging pendulum, so that I think has something to do with that. So okay, let's do it like this. So right here, I'm going to draw a little X on here. Let's say this is on its way up. I'm going to change color. Let's say this is on its way up right now. So forget this little bit of stuff at the beginning here. Let's just draw a vertical line right here to say that when we start, this is what we're interested in, right? So depending where we start, you can see that the offset, it becomes either a sine wave, or in this case, a cosine wave, or in this case, a negative sine wave, okay? But all that has to do with is where we're starting to look at our circle, right? So here's our unit circle. And we're going to say that this point on our circle is going to follow the motion of our oscillating pendulum, okay? So our circle is going to spin backwards in this direction. So there we go. And we're going to follow it as time goes by through these different positions. Okay? And we're going to realize that what we actually like map out on here is going to be the sine of those values, right? So you'll see I'm drawing r sine theta, okay? And you'll see that at maximal displacement positively, we have essentially r sine 90, which is just 1, right? 1. The full radius of this circle is equal to the displacement. And then we're just going to continue rolling around backwards until we get back down to here, okay? Where r sine theta is now 0 again, right? It's back to your neutral position. Keep rotating around, and we eventually get down to the bottom here. So this has gone up, back down, and now it's going to the bottom again. And then it's going to return right back around to where it started. So as this bobs, the circle rolls, and if we follow the sine of that value, okay, we will generate out of that a sine wave. If we record the values of r sine theta at all the angles we pass through around here, we generate a sine wave. Okay, so we're following the motion of the bob, and it will correlate to a spinning circle. And if we're drawing or we're mapping the sine of the radius at all these various angles as time goes by, we'll generate a sine wave that correlates to that. So if we choose to start at neutral, moving to a positive displacement, what you will find is that you get a sine wave here a negative sine wave here, and a cosine wave here. And you can imagine, to change these relationships, you just move the slider along. Now this has become the cos, right? With a negative cos, and then this becomes a negative sine down there. So if you kind of think about what you're learning in math class about how sine, cos, and tan relate, and the quadrants of your circle, what's positive, what's negative, and so on, you find that that's illustrated very nicely with an experiment like this. I just move my slider along, and you see how we move through these quadrants and how the relationship between these values changes. Okay, and we're going to end there.